Yeah, okay, good. So last lecture ended on making a remark about Johansson theory. So that's already one step away from just ordinary Yang-Mills. So let's talk about some other generalizations you can do. So if I stick within Yang-Mills theory, of course I can start adding matter. So this is my fifth remark. So matter can be included. And in general, that gives like a huge set of generalizations. So sometimes we call it the web of double copy theories. So of course you include the matter in the gauge theory, so you also have some web of gauge theories, but then you multiply them in various ways, and you get a web of double copy theories. So one example is if I have adjoint fermions in the gauge theory, or in Yang-Mills, say, then what happens is that you're forced to make this theory has to be supersymmetric, because the Jacobi identity is actually just equivalent to the Fierce identity that's needed for supersymmetry. So you get SUSY. And it's also obvious from the point of double copy, because if you have adjoint fermions, you have to multiply fermions and vectors. You're going to get particles which have spin 3/2, so you're going to get gravitinos. And it's well known that you cannot have spin 3/2 particles unless they're gravitinos. So SUSY is implied by spin 3/2. But of course you can also add the matter in the fundamental in Yang-Mills. And then you get a bunch, then there's less constraints. You can basically do it as you like, pretty much. And you get now matter in the gravity. Well, yeah. And in particular, if you have, you can also you can have some flavor symmetry in the gauge theory. For example, let's say you have some scalars which have some flavor symmetry, and then I have a trilinear coupling between these scalars. So basically some so flavor symmetry. For example, some lambda trace phi. We have to do phi, but they have some other global indices as well. Not sure what to call it. Also, let's call it F as well. So this is just a flavor structure constant. So if I do that, then in the gravity theory, actually I get gauge symmetry, or I get a gauge supergravity, or gauged gravity, I guess. So basically, yeah. So if you have a flavor symmetry, somehow gets promoted to a gauged symmetry after doing the double copy, and it's obvious because you're gonna. Well, the obvious thing to do is you basically double copy these guys with some Yang-Mills, and now this coupling is going to be the coupling of Yang-Mills in the gravity theory. Another way you can get gauge supergravity, which is quite different, is that if you have a Higgs and spontaneous symmetry breaking, then that leads to massive vectors in the gravity theory, typically, and that's also a feature of gauge supergravity. Yeah, sorry, I mentioned supergravity here because it's usually discussed in the context of supergravity. Okay, but I should say that the classification of what you can do, both in the gauge theory and the gravity theory, is very incomplete. So there's much to be done there.
Since you mentioned axioms,
Yeah.
so if something couples to the anomaly and the gauge side,
Yeah.
the axiom FF dual.
I don't know. I haven't thought about it. Yeah, but it's a good question. Yeah. I will mention axioms shortly, but not in the concept of anomalies. So yeah. So I guess I haven't thought about the anomalies. Yeah. So one question you can ask is, can you get all supergravities? Hold on. Let's 1 second. Can you get all supergravities, for example? And the reason why I say supergravities here is because they're more understood what you can do. And so the answer is that you can definitely get all the supergravities down to n equals 3 supergravities, so n equals 8, 6, 5, 4, 3. You can all get all of them in their ungauged version. Then when you get to n equals 2, there's a plethora of options. So I think, I'm not even sure if supergravity people have classified all the n equals 2 series. So there is less clear, but it does also look like we can get most of the n equals 2 series under some conditions and so on. But yeah, things are not so well known once you get lower supersymmetry, whether everything can be obtained. Yeah, a question, yeah.
This is kind of related to the axiom question.
Yeah.
Are these fermions in the fundamental representation chiral? Because if you get a eta prime, that also couples.
Yeah, you can definitely put in chiral matter in massless matter in the gauge theory, and even though it's anomalous, you can still work with it and do the double copy, because it turns out that in some cases the anomaly actually goes away after double copy, in the sense that you multiply two chiral things, but the product is no longer chiral, and that's actually needed in many cases, right? So we don't actually care whether this gauge theory is anomalous, because it's just a tool to get the gravity amplitudes, right? But that said, there could be something interesting, if I'm pretty sure that if you have an anomalous gauge theory and you multiply it with another gauge theory which is not anomalous, then the product will still be anomalous. So then the gravity theory will inherit an anomaly. But nobody has written a paper on that, so I shouldn't say too much on it. Okay, good. Anyhow, so that's basically doing various matter deformations. And I'm not going to say too much. I will say a little bit about QCD briefly. But before that, let me also say something about string theory. So this is my sixth remark. So you can also do new double copies for strings. So for example, you can even write the open string as a product, a double copy. So let me just do it schematically. So open superstring. So this is a product of two factors. One of them, if I go down to n equals 4, just to make it more clear. So this is n equals 4 superdiagonals times something that people have called Z theory, which is probably a misnomer because it's not a theory, so let me put it in quotation marks. So what is this? Well, you can write down the disk amplitude. Which looks like this. It was originally called Z, so that's why the name comes. So that's rho. So it's just some integral over the boundary of a disk with n insertions. Just a Koba-Nielsen factor. Let me not write it out. There's some orderings of the external insertions. And then there's some denominator factors here. and there's some, sorry, this is sigma, rho. There's some volume of the modular group. Anyhow, that's roughly how this disk amplitude looks like. Yeah, so what's sigma and rho? They're permutations. So of course I can insert my I can map the disk to a real line, and then of course the insertion is in some order. So there's an ordering here in the integration, but there's an additional ordering here in this denominator factor, which just comes from the correlation function on the world sheet. So you have two orderings, and they're very asymmetrical the way they enter.
So there is no momenta. Is this
in the Koba-Nielsen factor, there's momenta, of course, yeah. These are just Z, I, J, sorry, it's just a distance. And they're real, even though I call them Z, they're real. Yep.
And the Koba-Nielsen factor is just...
The usual one. What is it? Product of Z, I, J, S, I, J, I guess. I think that's what it is.
Well, it's just the string.
Yeah, it's a string. Indeed, I'm not the one who gave the name. So, first of all, this object was introduced in papers by Oliver Slaughter, Klaus Mafra, and Stefan Stieberger, and then the name Z-series was introduced in some other paper after that by some combination of those authors and John Joseph Carrasco. But you're right. So one difference compared to normal string amplitudes is that normal string amplitudes has this ordering and this ordering being the same. And furthermore, if you just do the Veneziano amplitude, I think this appears to 0 power. So this is basically the Veneziano amplitude with a shifted intercept. So basically making the scalar massless. So ordinary, the scalar is a tachyon. Here, the scalar is a massless particle. But in this, the new thing is that these two orderings are independent, and that's why it depends on two orderings. And that's why you can now, one of the ordering, you can multiply with a partial amplitude from n equals 4 superioring or really n equals 1 in 10D. And then you still have another ordering left over, which is this ordering, which is the usual open disk ordering. So that's why. So it simplifies. Instead of starting from some formula, which is more complicated, you can factorize it like this. Okay, good. Oh, and I should point out that I haven't really discussed it, but there's this thing called partial amplitude relations, which you can derive from color kinematics duality. And that's basically just relations between different orderings of the external legs. So in one of this ordering, the row ordering, it just satisfies ordinary relations that comes from field theory, whereas in the other ordering, it satisfies what's known as monodromy relation. So it's sort of a hybrid between string theory and field theory, sort of, in these two indices. And that's why this here is not the string theory KLT relation. This is a field theory KLT relation. Yeah. Okay, good. So that's one example. And then another really cool example is the heterotic string. So of course, the heterotic string is well known to be a double copy in the KLT sense. But here we can do it in a different way, which is also really interesting. So again, let's start with n equals 4 Yang-Mills. I guess I have dimension reduced to 4D for why not. And then you feed it basically the same product here, except that it's not this amplitude, but a slightly different one that people sometimes call the single value Z theory, I guess. Sorry for the sketchy equation. But this is still, so let's look at just gravitational amplitude in the heterotic string. So this is still not a gravitational amplitude. I need another factor. So the other factor is basically non-supersymmetric Yang-Mills deformed by a higher derivative kinetic term. So there's a d mu f mu nu squared plus some other stuff. But usually we call it the df square plus Yang-Mills. So you can write it like this. And so this is very different than a normal string theory KLT relation, which is between the bosonic string and the open superstring. And it makes things simpler, just like this made things simpler. You have this beautiful n equals 4 factor. This is maybe less beautiful, but it's also interesting. It's a theory that satisfies color kinematics duality. It has 1 over p to the 4 propagators because of this guy, but somehow in the product, these unusual propagators drop out because there's corresponding zeros in the Z theory. Okay, what is the single value of Z? So this is a particular mathematical operation which acts on the zeta numbers, Riemann zeta numbers, if you expand this out perturbatively. But you can also rewrite it as just a closed string version of this formula. So this is just a closed string version of that formula. And so the closed string version you get is basically you remove the ordering, you integrate over the Riemann sphere, and you have 2 such factors. Okay. Also, one funny thing is now you actually have alpha prime sitting in here, because there's an alpha prime here. But there's also an alpha prime here, because you cannot write down this unless you have a dimensionful quantity. So there's an alpha prime. I think it's sitting here, depending how you normalize things. And a funny thing, you can play some interesting games. I think it's 1 over. You can play some funny games. For example, I can take this alpha prime to infinity, this one to 0. Well, first of all, I can take both of them to 0. Then I just get back to n equals 4 supergravity, which is the low energy limit of the heterotic string in the closed string sector. But I can also take them independently. So I can, as I said, I can take this one to infinity. I can take this one to 0. And then I get conformal supergravity, which is very interesting. I don't know what the other limits are. Anyhow, so you can play some funny games.
What's the reference?
So this one, as I said, is Slaughter, Mafra, and Stieberger. They have several papers on it. This is with me, Slaughter, Chiadaroli, and Acevedo. It's a student of Nathan. But it's one of Oliver's papers, I guess. Okay, and there's other versions you can do of this, but these are the coolest ones. You can also do the bosonic strings this way. Okay, good. And then next remark, I'm still on the remarks, is you can do non-gravitational theories. So this is some work. I think you started with CHY, where they realized that you can do the nonlinear sigma model. So the nonlinear sigma model turns out to obey color kinematics duality, at least at 3 level. And then what you can do is that then you can take 2 copies of the nonlinear sigma model in your double copy. And then you get, so this is a scalar theory, so you get the scalar theory out as well. And this is a special Galilean. And another thing you can do is the nonlinear sigma model times Yang-Mills. And then you get theories of vectors, and it's abelian vectors. So it's Born-Infeld. And you can also dimensional reduce this theory, then you get some scalars here, and then of course you get a dBi, depending on if you have scalars here as external states or gluons, I guess. Anyhow, so these are just the more notable examples. And then, of course, you can take various factors, multiply them in some big multiplication table, which I'm not going to write out, but basically you can write any of your favorite gauge theories, like Yang-Mills, nonlinear sigma model, and add more stuff here, and then you have interesting theories in your multiplication table. I should say, though, that you have to be a bit careful, because this, for example, only works if all the particles are in that joint, because then there are certain rules that you can replace color factors with kinematic factors, and you're always going to get a product. But if you have other representations, then it's a bit more intricate. So yeah, anyhow. Yes?
So about this remark 6, this is all at tree level, right?
Yes, indeed. It's tree level and massless particles. So basically gluons and gravitons, but in string theory.
So given that the color kinematic duality was holds it at least at some loop level for field theory amplitudes, is there some hope that one could get higher genus string amplitudes at some construction like this?
Well, I mean, some of the string calculation have used input from kinematic numerators, specifically since n equals 4, of course, is the most well-known example at loop level. These have entered some calculations. So as I said, this genus tree closed string amplitude calculation at 4-point that was done by Yvonne Geyer and Ricardo Montero and another Ricardo. They used the known solution for the n equals 4 numerators and recycled them. So I do believe, I mean, so one point I said that this is not a theory, and the reason why it's not a theory is that all we know about this theory is this formula. And it's also probably not, I mean, nobody believes that such a string theory should be consistent in any way. But you can always ask, is there some way you can extend this formula? Can you extend it to one loop or whatever, right? And still get something reasonable such that you can still do a double copy at one loop. Okay, good. So unless there's any more question, the next thing I was going to talk about is some QCD amplitudes at tree level. So not QCD pheno, I guess. Let's leave it at that. Okay, well, I'm not going to talk about amplitude, but let's just discuss what you can do with QCD. So this is one example where you add matter to Yang-Mills. So matter, and just for reference, let me just give the Lagrangian. Okay, I'm not very careful here, but basically if you have many flavors, let's sum over the different Qs, the different quarks. And so we imagine here that we have some SU and C for the gauge group, and then we have some flavor group, SU and F. Okay, so the first claim is that color kinematics duality works at tree level. Even if I have my quarks in the fundamental, which is of course the appropriate. So this is fundamental. So now your color, well, let me say, so the color kinematics works. And by that I mean that you can find kinematic numerators which obey the same relation as the color factors. And your color factors are now functions of FABC and the generator, right? Because you have fundamental quirks. So the relations are a bit different. But you can still make it such that for every Jacobi or for every commutation relation, you have a corresponding numerator relation. And this is for different flavors, so you don't mix things which have different flavors. Okay. And when I say when it works, we have checked it up to 8 points. So up to 8 gluons and up to 8 quarks, external quarks. So there's no proof. Also no closed formula for the numerators. Okay. But assuming it works, the next question is, what is the double copy of this theory, right? Of course, you can say, well, it's just some crappy matter theory, you know, and I don't care. But, you know, QCD is beautiful theory, so clearly the double copy should be something beautiful, I guess, right? At least if you do it the right way. So let's just look at the asymptotic states. Well, maybe that's the wrong word for QCD. The fundamental states, whatever. So states. Well, states in the double copy. So first of all, we have the tensor product of the two gluons, which gives us the graviton. And of course, there's two polarizations if we're in 4 dimensions. So this is 2 times 2. And we know that there's 2 gravitons, so we're clearly missing some states. So the other states that we're getting is we're getting a B mu nu, which you can dualize to an axion, so that's a pseudoscalar. And then you get a scalar, so that's 1. So yeah, clearly this works. And yeah, as I said, you can always dualize the B field to something like, am I missing a, maybe I should contract an index. It's an epsilon, yeah, that's right. Sigma, epsilon, whatever, mu, something like that, yeah. Oh, let me call it A. Okay, good. Okay, so that's the particles in the joint, and then I separately multiply the particles in the fundamental, and I never do a cross term, right? Because I'm supposed to replace color factors. Well, I'm not supposed to. Yeah, I'm supposed to replace things in the fundamental with things in the fundamental and so on, so I'm not supposed to cross terms. So now I basically have the option of writing down a quark times a quark or a quark times antiquark. It's not going to really matter because in the end of the day I get rid of the color representation anyhow, so let's do quark times antiquark. So what do you get? Well, I can think of this as some complex field. So if I just count complex degrees of freedom, this is basically 2 times 2. And then I get some complex vector. And if this is massive, this is going to be massive. So this is going to have 3 degrees of freedom. And so this is basically a Procca field, complex Procca field. And then I'm going to get the complex scalar as well. Let me write it as tau. And we can, well, not sure why I did that, but basically it's very similar to, I can write it like this, I guess, just for well, suggestive. It's basically one complex degree of freedom, right? But what I'm trying to emphasize here is that it behaves very much like an axion and a dilaton as well. So we basically have an axion and a dilaton here, and the same thing here. The difference is that this one is, these guys are massless because they started out massless in the gauge theory, so I can only get massless dilaton and axion here. But since these guys can be massive, these are actually typically massive. So that's, yeah. I guess, the real world axion, if it exists, should be massive. So if you want to generate it from a double copy, this is the way. Often we talk about these two particles because they're often a problem, but they're always going to be massless, which makes it a bit harder for it to model something.
Why isn't that 5 degrees of freedom?
5?
Plus 1 plus 1?
Yeah, sorry, I count the complex degrees of freedom. Yeah. Yeah. Because, quarks really have 4 degrees of freedom, I guess. Well, at least if they are Dirac.
So it's real DRF on the top sum and complex DRF on the...
Yeah, I'm a bit sloppy, but yeah. The thing is that, all my quark lines are going to have an arrow. So I have choices how to align these arrows. But in the end of the day, the product is going to be an arrow, so it's going to be a complex field. Okay, good. Okay, so what can I do with this theory? Right now it kind of looks like a crappy theory because I have vectors and scalars. Well, so one thing I can do, what application? So one thing I can do is I can actually set my mass of the quark to 0. And then I can actually control which of these two states I get. Because I can basically now I get, instead of having like Dirac, I get some massless vial, and I can control the helicities very easily. So I can select which one of these two I want. And that means that I can actually just throw away this kind of trivially by just aligning my diagrams. And now I have these two guys. And now these are massless, and these are massless. So I can actually use these guys to cancel those guys. So the way to do that, very strangely, is to put NF to -1. So that means that whenever you have a closed loop of the quarks, you're going to put a statistical sign in front of them, and so they're basically going to act like Faraday-Popov ghost, right? So in particular, let's say I'm interested in computing, for example, like a one-loop 4-point amplitude in GR. So I can actually write that as a double copy of a Yang-Mills diagram. And a minus a fermion in the loop. And now it's a massless. And then I also multiply it with a fermion going the other way around. That way I'm going to make sure that the helicity cancel out and I get a scalar. And then there's two ways of doing it, which is that I can have arrow going up and down, or vice versa. But of course, they're going to give the same result, so that's just a factor 2. Yeah, so that's one way to compute a pure GR, which is not polluted by axion dilaton, and just subtract this. And we check that generalizes beyond one loop. We check that works at 2 loops, in the sense that there's no, you can worry about when you have many loops, how's it going to work, but you just put in your, one minus sign for each loop, which has a matter in the loop. Okay, good. So what else can you do? So you can consider classical scattering. So this is a bit weird because this is, it's QCD, so why is it classical? But let's do it. So let's consider, basically we want to look at the Procca field and do a Compton process. So this is basically this diagram. So we have, we have two gravitons here, and then we have, what did I call it, V and V. And classical basically means that we just make this field very massive, so that the recoil is insignificant. And you can ask, why is that interesting? Well, it's a spin 1 object which is very massive, scattering against two gravitons. You can ask, is that similar to a gravitational process that we know? And it turns out yes. So this actually is the amplitude for two black holes and two gravitons. And furthermore, since it's spinning, it's actually Kerr black hole. You might ask, how do we know what the Kerr black hole amplitude is? Well, it turns out that people in the last 5, 6, 7 years, they have matched field theory amplitudes with GR results, and they found that this amplitude matches the solutions that you get from GR. So in GR, what you do is you start from either some Schwarzschild background or Kerr background, and then you add perturbations on that. So you do what's called black hole perturbation theory, which is Reggie Wheeler in the scalar case, or Tukowski equation in the spinning case. And then you can compute this amplitude in the classical limit, and they match actually, which is quite remarkable. I should say that here we started with something which has quantum spin, and here you have to convert it to classical spin. So specifically, it matches this for up to s squared in the spin multiple expansion. So this quadruple. Sorry, what's it called? The quadruple moment in spin vector. So this is a classical spin vector. Okay, so that's a really cool application, and although it has not been proven that you can have more gravitons, I do suspect that since the double copy is quite well behaved, I suspect that you can probably add more gravitons here and it would not be a problem. What you cannot do, of course, is add more massive particles, because now you're going to get into trouble with the axion dilaton again, and that's going to, if you have a massless axion dilaton, it's going to change the long-range force between black holes. Yes, in fact, you might ask, how is that relevant for LIGO or something like that? Well, it's not relevant for LIGO because this process you cannot see. But you can use it as an input for another calculation. So you can do conservative 2-to-2 scattering, which basically looks like this. You have two incoming black hole, and then they exchange a graviton. And this process could in principle be observed, because you can imagine that, if there's some very dense cloud of black holes, they occasionally scatter past each other, like maybe around a supermassive black hole or something like that. So this process could in principle be observed. Well, if there's also a radiation coming out. But it also serves as input just to compute the effective potential between two black holes. So in that sense, it's actually useful for LIGO. So here, to compute this, all I need to do is I need to actually just compute the long-range behavior, which I can actually do by cheating a bit, because there's some virtual momenta here, and I can just say, well, it's small, so it's almost on shell. Like I can ignore anything that's q squared, so that's basically equivalent to cutting it. So I can basically just sew together two 3-point amplitudes, and I can reconstruct what this amplitude is. But for that, you don't actually need a Compton. But if you do the same thing to next order, then you're going to encounter a diagram like this, where you again can just assume that these guys are on shell. But here you have a contact interaction. And this contact interaction is actually something classical. So you need to figure out what it is. And you can get it from this amplitude, right? Because it's basically a 4-point amplitude there. Likewise, you can do radiation, which is basically gravitational waves. And so this process is also scattering. So you have two black holes. They exchange a bunch of particles. Let me just say that, well, represent that as a blob. But then they also emit a graviton. So this is basically, we're sitting here. This is LIGO, and looking at this graviton, which is a classical radiation. So it turns out also for this process, you can use this amplitude. It looks like you can't, because what I drew here is a 5-point amplitude. But you have to remember, again, these black holes are well separated. So you can always assume that at least one of this propagator is on shell. So I can for example, say that, yeah, here's a propagator here, which is on shell. It's a trick. It's not really on shell, it's really off shell, but it's small. So you can basically assume that small and being on shell is roughly the same thing. And then again, you have the Compton process here as a subdiagram. Yeah, so that's why this is useful, and it all came back to this double copy. And I should say that, I will come back to exactly what these amplitudes are later on, I guess. Yeah. Okay, is there any questions? Yep.
Why is the Yang-Mills one not getting squared?
Sorry, why is?
The Yang-Mills diagram or amplitude not squared?
Sorry, yes, thanks. Yes, squared, yeah. Not squaring the propagator, it's just the numerator. Yeah, you're right. Yeah. Any other questions? Okay. So, talking about black holes then leads to a different topic, which is the classical double copy. So let me say something about that. So this is work by Montero, O'Connell, and White. And I guess Donald will actually come here later in this program, I think. So what these guys observed is that if you just go to a well-known metric, which is called, well, it's really a metric ansatz, which is called the Kershild metric. Which looks very much like working on shell, because you basically expand your metric in terms of a flat piece and then a perturbation away from the flat piece, which people typically write like this. But the thing to remember here is that the perturbation is not small. It looks like it's small, but it's not. It could be large. And also another thing to remember that it's a product of two vectors. These vectors are not momentum. It looks like momentum, but they're not. They're more analogous to polarizations, but people wrote it like this, so it's always confusing. By the way, you might remember the plane wave solution that I wrote on before lunch. It looks exactly like this. I mean, two polarization times a plane wave factor. Okay, so what's important here is that this is a nice metric, but it's constrained. The k's are null. I think that's maybe why people call them k. So they're null vectors with respect to both the metric, full metric, and the flat metric. And this means that it's very easy to invert this metric. It's just, the inverse is just the same thing, but with a minus sign. And where raise and low are indices with the flat metric. Okay?
Do k or phi have spatial dependence?
Yeah, these are functions of your coordinates. Yeah, so yeah, it looks like momenta, but they're functions. Yeah. Okay, and okay, I'm not going to write up. I'm not going to. Yeah. So the cool thing about these metric ansatz is that when you write down Einstein's equation in the right way, it becomes linear. Even though it had made no assumption that this is small, the Einstein equation looks linear. Yeah, so Einstein equation. In H. Okay, and yes, and another thing, yeah. So why does it have to do anything with the double copy? Well, it looks like a double copy, but furthermore, once you have solved Einstein's equation, you can write up a gauge field, which looks like single copy, people call it. So basically, you instead of doing the double copy, you just remove. You remove a k. You do nothing to your scalar. This is some scalar potential, by the way, so this also depends on your coordinates. So you write up this gauge field, and now this satisfies Maxwell's equation. So in that sense, it's very similar to the double copy. You can complain a bit that it's Maxwell rather than Yang-Mills equations, but remember that it was effectively linearized. So you get something effectively linearized in the gauge theory as well. And it looks like almost this is too trivial to be useful for anything, but in fact the Schwarzschild solution and the Kerr solution both fits into this ansatz. So in this case, the k is actually just the radial vector. It's the radial unit vector, spatial vector, and then it's just unit vector in time. And the potential is just Newton's potential. So that's a very simple way of writing Kerr. And then the gauge theory gives the Coulomb solution. Yeah, well, so in order to see that, it's not obvious, so you actually have to do a gauge transformation to see that. So you have to do a gauge transformation, something like this, Q over 4 pi log R. And where's the 4 pi? 4 pi is just a coupling that you put in. Well, that's a coupling is missing here. Should be a coupling here and a coupling there, I guess. Oh yeah, sorry. So in this case, phi is equal to just Q over 4 pi R. Anyhow, it doesn't. What matters here is one of R dependence. The rest is just constants. Anyhow, so they're related, surprisingly. And as I said, this was just a gauge transformation to put it in the standard form, where you have no where you have no spatial dependence. Okay, good. How am I doing with time? So I said Kerr also fits into this. So let me say something about this. So in this case, the potential is a little bit more complicated. So it looks like this: 2gm over R plus a squared z squared over R cubed. And I should say, what is R? Well, first of all, A is known as the ring radius. So if you have, well, if you imagine there's a ring singularity, right, for Kerr, and I guess the spin is perpendicular to that ring singularity. So we put the spin in the z direction, and then there's a radius here which is A, and then this sits inside the horizon, I guess. Okay, good. Okay, so that's the potential, but you have to be careful here. We're actually using spheroidal coordinates here. So not spherical, but spheroidal coordinates. And then R is not your usual Cartesian R, but it's something that satisfies this equation. Yeah. So x, y, z are just your usual Cartesian coordinates, but R is the radial coordinates in the spherical coordinates, spheroidal coordinates. And that also relates to the fact that your k vector is again just a unit vector in this coordinate system, but because it's a bit more complicated, it takes this form. Yeah, so this is supposed to be the unit vector in spheroidal coordinates, written in terms of your ordinary Cartesian coordinates. Okay, and again, you can try to construct a gauge theory solution, and it doesn't have a name, so people just call it root Kerr, or it's not a well-known solution. So this is just A mu. Mu phi. So what is this? This is some massive spinning charged disk. I think it's not a known solution. I think that in this paper they're also discussing whether it even makes sense, whether it's, if there's a source to it, and whether this source is stable and so on, and it's a bit murky. But nevertheless, as I said, this classical double copy does sort of fit into the framework. Like the plane wave was on the same form. Yeah, think of this as polarizations. So it sort of fits together, although it's not obviously clear that it's exactly the same thing, because this is also effectively abelianized, whereas the amplitude's double copy is definitely non-abelian. Okay, any questions on that? I should say I'm not really an expert in this, and I think Kara in the audience has actually worked on this, so she's probably the right person to ask.
I think you don't mean massive here, right? Just the chart, right? The mass maps to the chart. I don't know what.
Yeah. Well, yeah. Well, it depends on how you think of it. Yeah, I mean, that's just a source, I guess. But if I want to think of it as a dynamical particle, then it should be massive, right? Just in the same sense as the Coulomb solution corresponds to just a very heavy, electron or whatever, right? So in that sense, yeah. So so maybe put massive in parentheses.
Okay.
Yeah. Yeah. So that's actually a good point. So these are just static solutions or stationary solution. They're actually not very interesting from the point of view of gravitational wave physics, right? Because what we want is dynamics, and dynamics gives radiation and stuff like that. And as I said before, the double copy of the Q to the amplitude did give dynamics with a spinning particle, which does match Kerr. So that suggests that these particles or these solutions indeed generalize in the sense that they generalize to dynamical objects, except that exactly how you go from this to the other picture is a bit convoluted. But let me discuss a bit more Kerr amplitudes. So now we go to dynamics. So Kerr black hole, 3-point amplitude. So this has been a very interesting topic, and it sort of started with a paper by Arkani Hamed and Huang. So Huang squared. So that's Yutin Huang and his student, which was also called Huang.
Double copy to what?
Okay, good. So they wrote. They were just developing some framework for massive spinning particles using generalization of spin helicity, and then they wrote down an amplitude which they really liked, which I'm going to denote by this. So basically, two particles which are massive and spinning, and then a graviton which is massless and has plus helicity. Well, you have to remember this is a graviton amplitude. So what they wrote is, let me write this, P1 minus P2. Well, I don't know why I write it like this, but anyhow, this thing squared, and then 1 to the power 2s over the mass of the massive object. Okay, good. Let's do one thing first. We can set the spin to 0. Then we only get this factor because this becomes trivial. So that's basically an amplitude of a massive scalar. You probably recognize that this is the Feynman rule for Yang-Mills coupled to a scalar. So the square is gravity coupled to a scalar. So this is definitely a double copy. This is also a double copy, even if it's less obvious. But you can just imagine that I take a product of a gauge theory amplitude of spin s over 2 and another s over 2, and of course in the product you're going to get twice that, or any way you're splitting the spin. So this definitely has a double copy form to it. And then Yeah, so Nima and Yutin wrote down this, and they call it minimal coupling, amplitude, and I think the name comes from the fact that it matches other well-known minimal coupling amplitudes for low spin. So, for example, if you do spin 1, you get a proca, and it matches basically the minimally coupled proca with gravity and stuff like that. Okay, good. And then some other people noticed that you can take a classical limit of this amplitude, and then it matches a well-known gravity amplitude. So we take a classical limit, h bar to 0, and then you get, well, let me just write, nothing happens to this factor, so let me just write the one, well, let me just write this, P1 is just a factor 2. But this factor here actually now becomes an exponential. So it's the momentum of particle 3, Lorentz vector times the spin vector over the mass. So this amplitude, well, this amplitude was more or less known in the sense that it was known, the current for it was known. If you just pull out the polarization, then you know the current, and this was known by a paper from Vines, this is from 17, this is also from 17. They basically write down these two papers at the same time, and they didn't realize they were the same amplitude. And the people who showed this are Guevara, Oshirov, Oshirov, and Vines. Also, there was a separate paper by Yutin et al. Okay, so one thing, going from this monomial to an exponential is actually quite non-trivial. And I'm not sure if I should spend some time on that. Maybe not, because I think this might be too technical. But the point is that in order to take this limit, you essentially have, you can ask, where's h bar in this expression, right? Well, we have quantized spin here, right? So quantized spin comes in units of h bar, right? And classical spin is very large in units of h bar. So basically taking h bar to 0 here, it actually means that we have to take spin large in order to compensate for the fact that h bar goes to 0. So this is essentially this infinite spin limit.
What is S mu in the exponential?
What this guy is?
Yeah.
Good. Yes. I should explain it. It's a classical spin.
Yeah, I was going to ask, is this
It's classical spin. It's essentially the Pauli-Labansky as a classical spin vector. So, I mean, of course, you can write it as some expectation value of some quantum operator. You can also dualize it, so you get some. You can also, so you can write it in terms of the Lorentz generator, and you can write it in various ways. But it's a classical spin vector.
Well, the particles 1 and 2.
You say for which particle? For which particle is it?
Yeah, it has to be the massive particle, right?
Yeah. So when you take the classical limit, you are essentially taking the mass very large. So essentially, the two massive particles have the same momenta, because there's basically no recoil, and they also have the same spin classically. So that's why I just write it. But yeah, you can think of it as the spin of particle 1, but it's the same as spin of particle 2. Yeah.
Thanks.
Okay, good. Yeah. Okay, good. How am I doing with time? Well, maybe I should sketch. Let me sketch the argument why these two expressions are the same, right? So first of all, we need to massage this factor 1, 2 a little bit. So one problem here is that we have a spinner which refers to particle 1, and we have a spinner which refers to particle 2, but then in this expression we only have an object referring to one of them. Like we can take this to be the spin vector particle 1. So we need to actually get rid of particle 2 here. So one way to do that is to write down something like, is to basically do a boost. So we can say that this valve spinner here is a massive valve spinner. We can write it as particle 1 plus a perturbation, which is basically P3 dot sigma acting on particle 1 over 2m. You might wonder, is this an infinitesimal Lorentz boost, or it's a finite one? It's actually a finite one because given that if you take higher powers of this thing, you're just going to get P3 squared, and P3 squared is 0 because it's null. So this is actually a finite Lorentz boost. But it's actually just a change of variables. So we're not actually doing anything, it's just rewriting it in terms of a boost. Also, we have to be a bit careful because we have to think that one particle is incoming, one is outgoing, and we really have to distinguish between that. And I'm just going to put a bar on top of this one so I remember which one is incoming, which one is outgoing. It has a specific meaning, but I'm not going to explain it. So now I can compute what this 1, 2 is. So it's going to be, I'm going to get a contribution which is basically 1 and then 1 bar. And then I'm going to get 1 over 2m, 1 sigma mu, 1 bar. Yeah. And then P3 mu. Okay, and so now it's important that I put a bar here because otherwise this could potentially vanish if they're the same state. But this is basically just a state and its conjugate state. And so if this is normalized correctly, this should just be 1. And this here is actually it is the spin vector. This is the spin vector. But it's not a spin vector. It's not a spin vector for a classical object. It's a spin vector for a spin 1/2 in the spin 1/2 representation. So it's a spin vector for a fermion rather than a classical object. Okay, good. Was there a question?
No, sorry. I just realized how it will exponentiate.
Yeah. Okay, so now maybe I go back over there so people can see what I'm doing. Okay, so let's write 1, 2 to the power 2s. So this is equal to 1 plus, this is, it's really the expectation value. Well, yeah, let me write it like this. It's really the expectation value of the spin operator. Okay, 2s. So now, in order to turn this into a classical expression, I just need to match the representation here with the power there, right? Because if I have a spin 10 object, I better use the spin vector for spin 10 object for a particle. So that you can do. There's a formula. So basically, spin vector as the operator in the spin S representation is basically 2s factorial over 2s, and this is to the power k as an operator. So it's 2s minus k factorial. Oh, sorry, factorial is outside here. And then s 1/2, also to the power k. And then there's some corrections. But those corrections are actually proportional to this momenta here. And so basically the corrections are going to be p squared, which is null, so we can ignore them. Okay, so using that, we can now write this as a sum. We can basically do a binomial expansion here. I write this as a sum from k equals 0 to 2s s. This is the spin vector p3 over m k 2s. It's messy, sorry. And this is still in the 1/2. See, that's just a binomial expansion. But you see that factor and that factor is the same. So it actually cancels. And you're left with an expectation value of the sum k equals to 0 to 2s s in the S representation of p3 over m 1 over k factorial. There we go. So you see that's an exponential now. E to the in the spin S representation dot p3 over m. Right. Okay, so we haven't actually taken the classical limit here. So this quantum object is equal to this quantum object. This is still like a quantum operator acting on incoming and outgoing state. But now the classical limit is really easy to take because in the classical limit we can use the fact that an operator square, the expectation value of an operator square is the same thing as the square of the expectation value, right? The variance is 0 when h bar goes to 0. So we can just use that when we expand this out, all the powers, we can just put the expectation value up here, right? So it's basically the expectation value up an exponential, and then p mu 3. Okay, good. And this is just the definition of the classical spin vector. So we can just say that is e to the s dot p3 over m, and s over m is the same thing as e to the a. This is the ring radius p3. Okay, good. So hopefully I convinced you that this formula holds. Okay, good. Yeah, so people use this to convince themselves that this 3-point amplitude actually describes a Kerr black hole, at least in the classical limit. But maybe even beyond that, because things looks very nice even before you take h bar to 0. And then from this amplitude, Akane, Hamed, Huang, and Huang they actually also used, they also computed the Compton amplitude, which I had before, right? The Compton is this process, which is just the 4-point equivalent, and you can basically use some factorization property. You can basically use BCFW on shell recursion to compute this one from this one. This is more or less what they did. I think they actually said that they just checked the factorization that was correct. But that gives a Compton amplitude. So maybe I write down the Compton amplitude here. So if this is 1, 2, 3, 4, you basically get the following formula: 1, 3, 2, 4, plus 2, 3. Oops. S t minus m squared u minus m squared. And then there's an extra factor here, which is some spinor helicity expression. 1, 4, 2s minus 4. Yeah, so I didn't explain what this spinor helicity expression here, but this is basically left-handed Weil spinor. This is a right-handed Weil spinor, and some of them are massive, some of them are massless. And this expression, it also looks like it holds for all spin, but you have to be careful because something goes bad here. So if S is larger than 2, if the quantum spin is larger than 2, oh, maybe do I have an error here? No, sorry, yeah. So if the quantum spin is larger than 2, then this exponent is positive, which means that this sits in the denominator. Whereas this gives spurious pole. Whereas if S is less or equal to 2, then this is well behaved. And so you can see that this is spurious because here is the physical poles, and this is something different. In particular, if P1 is in the plane spanned by 3 and 4, you get a 0. So this is basically some like a Gram determinant singularity, which is unphysical. So basically we know what Kerr is up to quantum spin 2, but beyond that we don't really know what it is. And I already showed you this spin 1 case, which was basically a double copy of QCD. Okay, and what do I want to say next? Yeah, so this is still an unresolved problem. There's a spurious pole here. You can subtract it out, but if you do that, you always have the ambiguity of adding local terms. So even if you write down a local expression, you still have the ambiguity. What is the contact term of this interaction? And people have made progress on it essentially by solving Tchaikovsky equation up to certain orders in spin, up to spin 6, for example. But you know, it's well behaved up to this, but starting at spin 5 and spin to the 6. Sorry, now I'm talking about the multipole rather than the quantum spin. And in that case, you get some trouble. There's some dissipative effects and so on, so it's a bit more complicated. Anyhow, I think the last thing I wanted to say is I wanted to just write a table for the series that double copy up to spin 2. Okay, good. So I call them the Kerr black hole EFTs. EFTs, because they're probably not the fundamental description. They're just some model which gives the right answer. Okay, so let's talk about, well, let's put the spin here. So spin S. So we have spin 0, 1/2. Ooh, I think I need a bit more space, maybe. One half, 1, 3/2, 2, and larger than 2, let's see. Okay, good. So let's write down some names here for the cur, and then what I call the root cur. So let's just write it like this: root cur. So this is the gravity, and this is the gauge theory. Okay, good. So for spin 0, it's just a minimally coupled scalar. Let's write scalar. So what I mean is just take a free scalar and couple it to the metric. You covariantize the free scalar, basically. Same thing here. Take a free scalar, covariantize it, and couple it to Young-Mills. It doesn't matter which representation it is, because you only care about one of them at a time. So here you would put in a Majorana, because you don't want to have a charged black hole, so you put in a Majorana. And here you have to have a charged particle, so this is basically Dirac. And for spin 1, I already mentioned that basically it's a minimally coupled Procca. So just take the free massive spin 1, minimally couple it to a GR, basically just covariantize the derivative. You can say, well, is it the same in the gauge theory? It turns out not to be the same, so I call it just a W boson. So what I mean here is that it has the same non-minimal couplings as the W boson has. So you might know that the Procca and the W boson have different Lagrangian, even in the simplest case of 3-point. Okay, good. And here, again, it's just a minimally coupled spin 3/2. So this is a Rarita swinger. For the gauge theory, it's actually not minimally coupled. So here I just call it a Gravitino. So what do I mean? You take an n equals 2 supergravity theory. You break supersymmetry that makes the gravitino massive. Then you throw away the graviton. and then since this n equals 2, you also have a graviphoton. So if you look at the graviphoton, gravitino coupling, it is the coupling that gives the right answer. And here, it's actually a Kaluza-Klein graviton. You might worry about the fact that if you do Kaluza-Klein and gravity, you get an infinite spectrum. But you have to remember that we only care about the Compton. So as long as we make sure that this has the same KK charge as this one, there's no pollution from the other states. Okay, so here for the gauge theory, this is just higher spin, meaning that there's no known name for this thing. It's also higher derivative. And the same thing here, higher spin, meaning that they're not really known in any meaningful way. But it's interesting that these low spin cases are well-known series. As I said, this guy here are just minimally coupled. So these are minimally coupled. Matter. And the same thing here. This is also minimal coupled. And this is non-minimal coupled in the sense that the interactions here are different. And this actually refers to the fact that, you know, when Anima and Newton wrote down their amplitude, they call it minimally coupled, and that's probably because they noticed that it agreed with usual minimal coupling. But I think when you go here to the higher spin, maybe it's a bit of abuse of terminology to call it minimally coupled, because these are really nasty higher derivative series. So you can already see this, that this is a one derivative theory, this is a two derivative theory, this is a three derivative theory, and so on. So each higher spin gives one more derivative. Okay, I think that's all I wanted to say. So if there's any question, I'm happy to answer them.
So let's thank Henrik very much.
Yep.
So where is this program going?
Oh, good. Well, one open problem is the kinematic algebra, of course, which I'd really like to know. I worked on it a bit, and it's a very hard problem, but it's a very interesting problem. Another problem is the higher loop numerators that we don't have working yet. So n equals 4 Young-Mills at 5 loops. N equals, just pure Young-Mills at 2 loops. Also, I mean, proving that it works at 1 loop, for example, there hasn't been, like, general multiplicity. That's something which would be interesting to do. Here, yeah, I didn't say, okay, so one thing I maybe skimmed over here is that people really like to know what is the correct completion of this amplitude. And it's known that if you remove the spurious pole and write down contact terms, it's no longer going to satisfy color kinematic stability. Or sorry, the root curve is not going to satisfy color kinematic stability, and there's no double copy. And you might wonder, why is that? Because it works really well up to spin 2. So why did it stop working? You can say, well, that's just how things are. When you have higher spin massive particles, there's no double copy. But that's not true. In string theory, you still have the open string factorization of the higher spin massive particles. So string theory is an example where KLT works even in a massive case. So you might wonder, the fact that it doesn't work, is it telling you somehow that you need to add something to make it work? Like, for example, so string theory obviously has not just one massive spinning particle, but it has an infinite number of them, and they're gonna propagate in this Compton amplitude. So maybe it's telling us that we need to add more spinning particles, because of course even for a black hole, there's not just one black hole of one spin. They can have any spin, right? And they should be in the intermediate channel. So maybe there's something that can be done there where double copy can help. What else? I think it would be good if we can find more applications towards pheno, for example. So, for example, QCD pheno, like, if you want to do 3-loop QCD, could this help? Could color kinematic duality help in some way? I think 2-loop, currently people are working at 2-loop, 5-point, and so on. And there, the Feynman rules just work fine. You don't need to use color kinematic duality. But there's some loop order, you might need them. And then maybe could be useful. What else? Yeah, I've been telling you a lot of cool things, but then I said, we don't really know why it works, right? So, it would be good if we can understand. You could say, well, it's all coming from string theory, but that's just, why does why does string theory have this factorization and so on.
String theory is a simple physical argument.
Yeah, you have a yeah. Yeah, it's yeah, but you can also say why does it work in many different cases that not obviously related to string theory, like the nonlinear sigma model. I also mentioned this magical octonionic supergravity. It seems to say, that, I mean, probably many of these cases where it works in field theory, doesn't have an obvious qubit completion in terms of string theory. So, why does it work for things which are not obviously related to string theory, or like we have some mathematical details, but we don't really have a physical intuition other than maybe string theory, right? Yeah. We don't. So I mean, for example, the kinematic algebra. I'm not sure if string theory has something to tell us. I mean, I asked a few string theories whether they can help, but it wasn't obvious. But I mean, that's one of the big open questions in the color kinematics duality, so we'd like to have some help there, I guess. Yeah, I don't know. I mean, does somebody have any addition?
Well, the other new development is surfaceology.
Surfaceology, yeah. Yeah, so
That might be very connected to this.
it is connected, yeah. So one of the problems of going to loop level is that it's actually very hard to label your loop momenta, because all of these Jacobi relations are basically taking place at the integrand level, and so you need to have very good control of your loop momenta, and that's basically what Nima and friends have been working on. How do you make a global integrand which have like a global loop momenta and a global Feynman parameterization, and that's what they've been doing in this surfaceology context. I mean, their solution is basically that you sum over all possible ways of labeling your graph, which basically gives some infinite sum. And I guess you could also do it here, but it naively seems like you're trading one problem for another problem. So I'm not sure if we can use it.
Well, that's dealing with how you break up the loops, but
Yeah.
there is this shifting of
Yes, so they shift their scalar amplitudes, and then they get gluon amplitudes out of it, yeah. So that's very interesting. They also have some zeros that they noticed in their amplitudes, which I think they're related to poles, but Shruti has been, where's Shruti? There, yes, she's been working on it, and you showed that it's actually related to color kinematics duality. You can derive the zeros, or at least if you assume color kinematics duality, you can derive the zeros, maybe not the other way around, yeah. Yes. So there is connections there.
Could you state that again?
If you have a color kinematic dual theory, then you have these zeros that...
Hidden zeros, yeah.
Yeah, the hidden zeros that you might
Yeah. Also, they're working on this trace phi cube, but that's basically just the diagonal element of the biadjoint phi cube. It's not a huge difference, I guess, yeah. One thing is the classical solution. So I think there's been a lot of work on the classical solution, but I think most of that work is you look at a known solution in GR or in gravity, and then you map it to a new solution in gauge theory. But it would be better if you did it the other way around. If you find a gauge theory solution and you just uplift it to a gravity solution. I think there are some examples of that. Somebody pointed out that in 3D topologically massive gravity, you can actually go from the gauge theory solution to a new gravity solution for basically in the dilaton. You have a dilaton in 3D. But I think that I don't know if you know any other examples. Yeah. So there, I think there's a lot of room for improvement, maybe to find maybe new solutions. Yeah, I think that's enough for wish list, I guess.
Can you get this exponentiated amplitude from some double copy of like a classical limit of a root Kerr amplitude or something?
Yeah, I mean, you can also do the classical limit of the root curve, and it basically looks. I mean, it's just this. So in that sense, you can say that it's a double copy also at the classical level, because I mean, all you're going to get is 2 exponential, but of course, this is going to sum up. So if you just say that, well, if the 2 spin vectors point in the same direction, and you sum them, well, you can call it 1 spin vector, I guess. 3 points is a little bit too trivial. I think it would be more interesting if you can do something like that at the Compton level, because there we don't know what the amplitudes are, so it would be more useful there, I think. Yeah. Oh, there was one more question. Yeah.
I was just wondering if you have a comment on whether or not there's an off-shell analog of color kinematics duality
for matter?
Lagrangian level. Just at the level of the Lagrangian, can you see it as a symmetry?
For Yang-Mills with matter? I think adding matter doesn't really help. I mean, already for the pure Yang-Mills, we don't know how to do it. Adding matter does not help. So, so I showed you the Chern-Simons case where we know everything for pure Chern-Simons, but there's no amplitude. So you can fix that by adding matter to the Chern-Simons, so you get the Chern-Simons matter, and then you can actually do some really cool things. You can do like an n equals 4 Chern-Simons matter square, and that's actually n equals 8 dBi. So this is in 3D. So that's an example. That's an example where the double copy of a gauge theory is not gravity, but is dBi. But yeah, so the point is that you add matter, you actually lose the nice off-shell properties. So now, yeah, so the matter did not help. Yeah. This theory is also known as Gay-Otto-Witten theory, I guess.
Perhaps we should give Henrik a double thanks.